start and see, looking at. So we did it till here, and now I would just like to tell you about two things really. Wait a second, I could check this. Just a second, please. Okay, well, that's cool. Anyway, so considering the whole thing, then let's move to the next thing I want to teach you. So basically the two things that you guys need to remember, one is whether you draw it or don't, it's fine. I just want to show you the difference between the motor and the generator and how they are like all together with seemingly about the same kind of assembly. They have two different functions altogether.
So your voice is low.
My voice is low? Okay. Is it fine now?
Yes.
Okay. Sorry, I'm just a bit sleepy today. Okay. So the main difference between generator and the motor is that both contain this coil. That's fine. However, in a generator, the coil is basically going through sort of in this axis where it clamps up to make like full rings. So like this, and then these two wires are connected to an ammeter or a voltmeter, doesn't matter. That's right, voltmeter in fact. Whereas in this arrangement, the motor uses a different kind of assembly where it is connected to split rings. And then sort of iron. We also have carbon brushes here. And then a positive terminal and a negative terminal, doesn't matter. Okay. So what I want you to understand is that of course this particular part will have n number of coils, and that's basically the same on both of them. This basically provides you alternating current induced, and these are called the slip rings. These are called the split ring commutator. This is all the knowledge that you've taken in, right, from other real thing. And then of course you see the magnet and everything else, that's the same from the O levels. So it's assumed that you should remember that this generator uses Faraday's law of induction, and the motion, basically when you move it, induces EMF as the coil cuts the magnetic field constantly. In fact, let's write constantly when it is moving. That causes a change in magnetic flux linkage per unit time, like that. The motor, however, uses Fleming's left hand rule, and basically current produces motion. So that's because there is a force acting. So that's mainly this. So in generator, the motion produces the EMF. In motor, the EMF basically helps it to move. So that's basically the opposite thing, and that's why they're designed different. We don't really need to know why there's a commutator, why there are slip rings. We just need to understand that why these two different laws are being applied here. Okay, like that. However, going through the generation part, we're just gonna look at something very, very important. So if you really see what's happening here, so suppose that we have a wire like this, or conductor, it does not really matter what is it, and it's like just a conductor and connected to nothing really. So suppose this is the length of the conductor. Say this is the point P, this is the point Q, and now there is a uniform magnetic field that is going into the page like this. And what you're going to do is you're going to move this in this direction with a velocity v. So suppose the magnetic field here is 2.0 Tesla. So you just need to remember that when a conducting rod is moved perpendicular to through the field through a magnetic field, then what really happens is the rod's electrons experiences a magnetic force F because velocity v, right? Because of this velocity that we're moving it. And the force, we know already that this force comes from the this equation BeV that we have done in the previous chapter that you might remember. Now if you look at the whole scenario here, you can use Fleming's left hand rule and you'll see where the force will be. So if you see the index finger will be towards the screen, the middle is going towards the velocity, so my thumb is upwards. However, because these are electrons, so they're going to move in the opposite direction like this. Basically that will make this side as positive and this side is negative. You need to remember that. Okay, do you guys understand this? So these electrons will travel downwards due to magnetic force, and that's according to the Fleming's left hand rule. So as they move downwards, there is a drift inside the rod that makes rod's one end positive and the other end negative. And this is causing a potential difference to be generated. So of course, if you put a voltmeter across it, like I'm going to show you this. So you see, if you let me copy this. In fact, well, I'll just copy this part only. Let's move it a bit here. So now if you connect a voltmeter right here, you would actually find a potential difference P and Q because the electrons have drifted towards the other side due to the force, right? And from this point onwards, we can actually find the work done by magnetic field on these electrons. Now, so we know that the work done is given by force times displacement, and the force on these electrons were equal to BeV, and the displacement they've moved is actually the length of the wire itself because they've gone down like this. So that's one part that I need you to remember. The other thing is that the current is the rate of flow of charge, as we know. Basically, the charge moving is E, and with respect to time that would be the current. So as the electric field is generated, because now they've gathered, and top and bottom, so electric field is generated. So we know that electric field is given by force per unit charge, and in this one the charge is an electron, so I'm writing this. And electric field is also the voltage that is between P and Q and the distance between the two points from here till here. So that would be L, like that. So what you want to do is, you can actually make PQ the voltage as a subject, and then we're going to write FL over E, just like that. And because from the very first part we know that F is BeV times L E, so I just replaced F here. And now you might realize that E and E will cancel out, so VPQ will be equal to BVL, and that's basically what you need to understand, that this is the formula that will tell you about a moving conductor. Alright, so this would be the potential difference across the top end and the bottom end of the rod. This is basically the magnetic field strength. This is the velocity of conductor, and that's the length of the conductor. So it causes this potential difference to be created. Is this clear? Please let me know if you do not understand this. All right. Now,
Sir, could you show the diagram again, please?
This one?
Yes, sir. Okay, sir, done. Thank you.
Okay, that's cool. All right, now. Now, let's move to a little bit of summary that I just want to tell you, and that's, if you remember this, you will, always be happy. So I'm just going to write a side note here. And the side note says, okay, here. So we're going to talk about motor in general, and then we're going to talk about the generator. So for a motor, remember that the force is given by B, I, and L. That's the formula, and that's basically represents the Fleming's left hand rule. So what we need to understand is that providing current to get force or torque, right? That's what we need. So whenever we need to find the torque is given by the force times the perpendicular distance, and that's for the motor only. However, for a generator, you need to remember that because of the Lenz's law, you use Fleming's right hand rule, which means basically it has the same rules. It's just that you use your right hand to do it, to find direction of induced EMF or current. Okay, and this is basically you need to remember considering conventional current. This is only for that. And then basically it does not use Fleming's left hand rule. Basically it uses Faraday's law, which is that EMF is equivalent to change in magnetic flux over change in time, and this negative sign shows that it will be, the change will be opposed. And just remember that this basically depends on that we are providing force to get voltage or current. Alright, is it clear? Let me know if you have a question here.
So why can't we use Faraday's law for motor?
Because motor is not inducing the current, we are providing the current so that it should move. Do you understand what I'm saying? So we do not seek to generate current, we're just seeking to move it, and to move it we need electricity. Understood?
Yes, sir.
That's the difference in between these two. Okay, so in 10 minutes please rejoin the class. And now let's move to the next very important thing, and that is an experiment which is basically regarding oscillating magnet in a coil and the effect of Lenz's law on it. Okay. Now, suppose that you got a magnet attached to a spring, okay, like that, north and south, and now it is moving in this direction, and you want to it will move basically within this in and out of this particular cylinder, which is wrapped by a solenoid. Like this, and now we have an ammeter here, and we got basically a resistor connected to it, okay, like that. So on the other case, let me just copy this. So if the movement is like upwards, like this, so these are like two different concepts. So of course when it's moving down, we've learned that this will induce a north here just to oppose it, and when it's moving up it is going to induce a south here to oppose it. And basically the north is induced because the current starts to move within this, and the ammeter shows reading, and the current will then, when it's going up, it will be induced in the opposite direction. So right hand grip rule can help you find this. However, what you guys need to remember is that there is something that this resistor is going to do as well. So let me just explain to you now. So it can be noted that the induced poles try to oppose the motion of the magnet. Therefore, the kinetic energy of the magnet is reduced by work done against overcoming electrical, and we could say magnetic damping. Now you guys might remember damping is basically the dissipation of energy, right? Dissipation of energy, like that. Now, so
Sir, I don't get this.
I'll tell you. You see, when the magnet is moving down, right? And if the magnet is moving down, the knot that is created due to the Lenz's law, it is trying to slow it down because it's opposing, right? Don't you think so?
Yes, sir.
So with slowing down, basically it is causing electrical or magnetic damping. Don't you think so? It has to do, the kinetic energy of the oscillating magnet has to do work against the force of magnetic field. Don't you? Do you agree to this?
Yes.
So what happens is that hence the magnet would come to rest after performing few oscillations. That's what we expect, right? Because the current is always like it's going up, so it will try to slow it down. It's coming down, it will try to slow it down by opposing it. Understood?
So basically, it's dissipating energy to overcome the work done, right?
Overcome the forces due to electrical and magnetic field that's generated here. Understood?
Yes.
Now, if there was no resistor, like there is a resistor right now, if there was no resistor, it would even slow down faster. The reason why I'm talking about that is because if the resistor is placed in the circuit, the magnitude of induced current reduces, because resistor, basically what happens is it's overall increasing the resistance, which is reducing the overall current that is generated in the coil. You guys agree to this, right? So if there is less current, then of course there will be a smaller opposing force then. So hence now less energy is required to overcome the lesser opposing force. You get my point? So again I'm going to explain this. If there was no resistor, the current that is induced within the coil will be larger, right? If the current is larger, then the opposing force, which Lenz's law has told us, will also be greater. Everybody agrees to this? Now, putting a resistor in the circuit would cause the current to be less, like induced current to be less. If there is less current, so it won't be able to make a very strong pole, which means now you need to do less work done to overcome that small force. Understood? So if there is less force, then as a result, the degree of damping reduces, allowing the magnet to oscillate for a longer period of time. Okay. Aman, do you understand this? And Suman and Hasan Atik, Gatika.
Yes.
Yes, sir.
Okay. All right. Now, so if I make the graph of it, like the oscillation graph, because this basically comes from the same chapter of oscillations, SHM, if you remember this. So basically, with a resistor, if the oscillations were like this, right, initially, so it would basically damp up really fast, like this. This is without the resistor. Without the resistor, because the current will be more, so it will cause a stronger opposing magnetic field. But with the resistor, basically it is going to show you a much more basically lesser damping than before. So this is going to be with a resistor. The reason is that the current will be low because of the resistor, which means opposing magnetic field won't be that strong. And if the magnetic field opposing is not that strong, it means that it's gonna help the magnet oscillate a bit more for a longer period of time. So that's how it works, right? Any questions now? Okay. Now, in certain situations, what we need is we don't want current to be generated in certain situations, okay? And we got to control that, unwanted current induced because of, the magnetic field. And it could be just, the electrical or magnetic fields in the surrounding that might affect us, so we can actually help us doing a particular thing that can help us, reduce that effect. And basically, the unwanted current that we see, or the electrical magnetic interference that causes unwanted current, these unwanted currents are called the eddy currents. Okay. Now, suppose in an experiment, just to show what we're actually doing, suppose there was a magnetic field in the surroundings, although we don't want it, but there is one. So there is a north here, and there is a south here. It's going like this. And we want a conductor that's basically the conductor itself. this is a pivot, and about this pivot the conductor is moving back and forth like this. Okay, so this is our conductor. Now when the conductor is moving, although we don't want current to be induced, we just want it to oscillate. So of course the oscillation will basically cut the magnetic field, right? So we can write that when a conductor is placed within the magnetic field, pivoted, that's right, at point P, let's write P here in fact, not here, okay, pivoted at point P, then what happens that as it oscillates perpendicular to the field, okay, so as it oscillates perpendicular to the field, we need to remember that there will be an induced current generated inside it. So this unwanted current, we don't want to induce it, we just want the conductor to just oscillate, is known as the eddy current. Okay, and that's one of those things which happens regularly. And then what happens is that this current causes damping, as we have seen in the previous experiment as well. So if continuous motion is required, then what you're going to do is we increase the resistance to reduce the eddy currents. Okay, and basically increasing the resistance, this process, the process of increasing the resistance is called lamination. Lamination means, like, you when you used to go to you were like in early okay, okay, I'm sorry, there was a connection issue here. So you used to put plastic lamination on this, and basically lamination means that you're putting sort of a material inside that is an insulator. Oh my god, there is thunderstorm now. So that would cause basically the overall resistance to increase. Do you guys understand now? Suman, Aman, Karthika?
Yes, sir.
That's good.
So can you repeat the lamination part?
Okay, lamination is like, let me tell you this. So Karthika, let's suppose we want this conductor to move, right? So what we will do is we'll cut the conductor into many sheets. Okay, Karthika? Sheets mean that we're gonna slice it up like this. Okay, Kartika? And then each slice, like between each slice, we're going to put an insulator, like rubber or piece of plastic or wood or whatever. Do you understand what I'm saying?
Yes, sir.
So what will happen is that it will increase the overall resistance of this. And if the resistance increases, then the current that is forming, like the current that's like moving inside, because of the induction, basically the size of the current reduces. And because of the size of the current reduces, now the opposing force will be smaller, and hence it will allow the conductor to oscillate for a very, very long period of time. Got my point?
Yes, sir.